Okay, so previously we defined a relation from a partition of a set and observed that that relation was an equivalence relation. We want to sort of aim for a converse of that in this section. So I want to study equivalence relations and eventually get to the fact that every equivalence relation defined on a set produces a partition of that set. So to do that, I need to start with the notion of an equivalence class. So let's first assume that we have an equivalence relation R, so that is a relation on a set A that is reflexive, symmetric, and transitive, and take any element, little a, of A, and gather together all the other elements of A that are related to it through the relation. Then gathering those elements together into its own little set is called an equivalence class of A. So for each of the elements of the set A, we can do this and hence sort of call out a bunch of subsets of the set A. Let's explore this notion through sort of the most common example of an equivalence relation. Let's do congruence mod 5, but we could do congruence mod any integer that we like. Okay, so let me review what congruence mod 5 means. So the set that we're interested in here would be the set of integers, and then we say n is equivalent mod 5 to m if, well, there's a number of different ways that I can say this. Off here to the side, you'll see how the book sort of defines this. They say that the difference of m and n is divisible by 5. Okay, so this is written in a number of different ways. You can say n is equivalent to m mod 5. I think most conveniently I like to just tuck a little 5 down there by the equivalence sign. Oh, by the way, you can get the 3 bars if you type equiv in equation editor. That's the LaTeX for that symbol. And this is also the same thing as saying that the remainder upon division by 5, if you divide n by 5 and you divide m by 5, you're going to get the same remainder. That's another way of saying that n and m are equivalent mod 5, or congruent mod 5. Okay, so that is the relation. It was previously proven to be an equivalence relation. Well, I mean, the book proved that congruence mod 3 is an equivalence relation, but it goes the same way. What do we want to do? Let's go ahead and list the equivalence classes produced by this relation. Okay, so for any integer, I can write down all the other integers that it's equivalent to. So let me start with, like, how about the integer 10? So 10 is an element of the set A, or Z here. And what are some other numbers that are equivalent to 10 mod 5? That is, if you take 10 minus another number, how could it be divisible by 5? Well, I think 10 itself would be such a number because 10 minus 10 is 0, which is divisible by 5. And then if you subtract any multiple of 5 from 10, 10 being a multiple of 5 itself, you're going to get a multiple of 5. So all of these numbers, I'm not listing them in a very good order here. Sort of got them backwards, but what I'm getting out of this is that the equivalence class of the integer 10 happens to be all the multiples of 5. Let's write that out in an efficient manner. Okay, I'm also going to get a picture drawn off to the side over here. So I'm actually going to draw all of the integers as dots, and I'm going to go ahead and color in the equivalence class of the integer 10. So I'm going to color in all the numbers that are multiple of 5. 0, 5, 10, 15, 20, and so on. Okay, and let me make an observation about naming here. Gathering together all of the integers that are equivalent to 10 mod 5 is exactly the same thing as gathering together, for example, all of the integers that are equivalent to 0 mod 5. So I could also call this set the equivalence class of 0. In fact, that's a typical thing that occurs with the naming of equivalence classes. You can name the equivalence class according to any representative of that class. So if you gather together all of the stuff that's equivalent to 10, and that ends up being the same as gathering together all of the integers that are equivalent to 0, then this one set is named by both of these two different names. Like, every single integer is in an equivalence class, but there's lots of integers that share an equivalence class. So when I'm trying to go through and write down all of the equivalence classes, it's not like I'm going to have infinitely many, because many are going to be repeated. So I'm just going to try and be clever about how, the next integer I decide to consider, so that I can get all of the equivalence classes written down pretty quickly. So I'm going to move on to the integer 1 and try and gather together all of the integers that are equivalent to 1 mod 5. So again, coming back up to the definition, that means I'm looking for numbers that I can subtract from 1 and result in something that's divisible by 5. So 1 itself would be in there. Let me write this in a smarter way this time. So 1 would definitely be in there. And if I had 6 minus 1, that would give me 5, which is a multiple of 5. 11 minus 1 is 10, which is a multiple of 5. And so on, like this. What about some negative numbers? If I take negative 4 and subtract 1, then I get negative 5, and so on and so forth. As before, let me color in all of the numbers that are equivalent to 1 mod 5 in the picture, just for a visual, and just make the observation that this set right here has many different names, right? This set is also the equivalence class of the integer negative 9, and in fact, it is the equivalence class of every single number that's in that set. So it has many different names. Okay, let's get the other equivalence classes that there are written down. And after I get these written out, I hope that we agree that this is all of them. Every single other integer is going to be in one of these equivalence classes. Okay, so there we have it. I've sort of listed out each of the members of each of the equivalence classes that there are, and I colored, it looks like I missed one color here. Hold on, let me get that dot. Okay, so I colored in all of the equivalence classes off to the side on the image of Z. So a couple things that I want to say about this. Notice that each equivalence class is a subset of the set A. So in this case, each equivalence class is a subset of the integers. And here, many different integers were in the same equivalence class. And it makes sense because there are many numbers that are, for example, equivalent to 2 mod 5. Here's some other observations. No two integers are in two different equivalence classes. Like, you can't be equivalent to 2 mod 5 and also be equivalent to 3 mod 5. So the equivalence class of 2 and the equivalence class of 3 are disjoint subsets of Z. And in fact, if you take these 5 sets all together as a collection, you would call it a mutually disjoint collection of subsets of Z. None of them hit each other. Moreover, every single integer is equivalent to something mod 5, namely itself, and many others. So every single number in the picture got colored into one of these equivalence classes. So another way to say that is that the union of these 5 equivalence classes is all of Z. And observe that that's exactly what it takes for this collection of sets to be a partition of Z. And that's sort of the converse that we were aiming for with this example as a motivator. Given an equivalence relation like congruence mod K, you can define a partition of the set. So if you gather together the elements of the set into their equivalence classes, those classes will form a partition of the set. So that's the theorem that's listed here now, theorem 834. If you have a partition and you define, if you have an equivalence relation on a set and you define the collection of equivalence classes, that will be a partition of the set. So there's a couple things to show here. First, the union of those equivalence classes is all of the set A, and that the collection of those equivalence classes is mutually disjoint. So no two equivalence classes hit each other. So let me just argue one of those things, and you can argue the other, or just read from the book. Okay, so suppose we have an equivalence relation R on a set A and gather together all of the equivalence classes. Remember that each of these equivalence classes is a subset of the set A. Gather them together and put them in a bag. I'm going to call that bag P. What we'll prove is that P is a partition of the set A. So there's two things to show. First, that the union of sets in P is all of A. And then secondly, that given any two equivalence classes, their intersection is empty. So I'll go ahead and just prove this first part, and you can either read about the second part or work it out for yourself. Okay, so first off, since P is a collection of subsets of A, it's already obvious that the union of the sets in P is a subset of A, because if you take a bunch of subsets of A and union them together, then you're certainly going to get a subset of A. We're trying to prove equality here, and since subset in one direction is obvious, the only thing left to show is that A is a subset of the union of the sets in P. By the way, if P is a collection of sets, you can represent the union of those sets just by putting a union symbol in the collection. So what I've argued already is that since P consists of subsets of A, this inclusion is already obvious. But the other direction is the one that takes some thought. Oops, that's not the other direction. Okay, and then how do we prove something as a subset of something else? We let X be in A. Okay, and what are we aiming for? I want to show that X is in the union of P, which means I need to find one of the members of P that it is inside. So I need to find an equivalence class that X is in. Well, one candidate for an equivalence class that X would be in is its own equivalence class. So why would it be the case, off to the side here, that an element of A would be an element of its own equivalence class? What is it about the relation R that guarantees this? Well, since R is reflexive, it's reflexive, symmetric, and transitive, but in particular it's reflexive, we have that X is related to itself, right? In other words, X is in its own equivalence class because its equivalence class is all of the things that it's related to. So we have found a member of the part of the collection P that X is a member of, hence X is in union P.